Okay, great. Thank you. Please, I wish I were there. I wish I could have time to travel there. On the other hand, I think about those conferences 100 years ago where you see these scientists, or you see Ramanujan, sitting in Cambridge, and how it took months, a month to get from India to England. Um, and how you could only participate if you were actually physically there. And so, on the one hand, I'm sorry. On the other hand, I'm glad that, the world has shrunk this much that I can still participate uh, in this school. And I really hope you'll ask me questions. And if not, while I'm talking, you should certainly send me email. So, what I wanted to talk about today and tomorrow is applications of minimal surfaces and how they come up all the time in physical systems. And, I've been thinking about it. Is this because there's some deep connection to minimal surfaces, or is it that maybe geometers and geometry just ask the right questions? Maybe it's just the natural language for things. So here I have a picture of Plateau, who does anyone know? Does anyone know uh, why Plateau is famous in Belgium? Anybody? This is a picture from a stamp. This is a stamp in Belgium. And you can see his bubbles there and all that. But do you know what he's famous for? Anybody? I can see you, so you're not shaking your head. You're not doing anything. Yeah. He was the one who discovered persistence of vision. He discovered that you can make a movie by showing showing pictures at a rapid pace, and discovered that your eye blended them together into vision. So he is actually credited as the grandfather of movies. And there's a festival every year in Belgium to celebrate him. It's a cinema festival. So that's how he's known to the public. To us, of course, he's one of the people who sort of proposed this idea of minimal surfaces. And let me remind you of a few. The first one there on top, let's see how this works. Right, the first one there on top, right, is the catenoid. And the catenoid is kind of an interesting surface. If you take a metal ring, two metal rings, and you put soap, you put soap between them, you don't just get a cylinder. A cylinder has actually more area. The soap is trying to minimize its area by or decrease its tension. And so what it does is it actually comes in and makes this waste. And this actually uses less soap. However, don't be fooled. If you take the rings far enough apart, right? If you move them far enough apart, all you get is you get two discs of film. Right? So the picture you see on the left, right, this guy here, is already lower area than the area of the two discs on the top and the bottom. But when it gets too far apart, it pops and becomes two discs. The next surface, which I'll talk about a lot in the next 2 days, is Riemann's minimal surface. And Riemann's minimal surface is cool because if you took a cross section of any one of them, it's always a circle. The cross section, right, perpendicular to this axis is always a circle. So what Riemann's minimal surface is a sequence of circles that grow up and down as you go along this axis, which I'll call Z. The circles get bigger and smaller, and their centers move. Excuse me, and their centers move around. But it just sweeps out circles, and it's a minimal surface. and then I think I saw that there were some more talks this week where it turns out that there's another class of minimal surfaces, these triply periodic minimal surfaces, and they've actually become really important for devices and heat exchangers because even though they have this funny word minimal surface, sometimes they're actually large area. And so sometimes these minimal surfaces, these triply periodic ones, give rise to structures that have a lot of surface area. And surfaces are where heat is transferred. It's where chemical reactions occur. And so if you want to have something that has a lot of area packed into a very small volume, minimal surfaces are a way to go. And so people have been making these heat exchangers now, for instance, that are filled with the gyroid, okay, which is a kind of triply paired minimal surface. All of this will, I hope, be explained. So let me just tell you, there's a bit long history. Does anybody know who any of these people are? I'm coming trying to interact with you from, 7,000 miles away. Anybody? Can you identify any of these people? Yes, go on. I see you. Gray shirt. Oh, I can't hear him. Shout it out. Oh, okay. Shout it out.
One is Euler on the left down and
Yes,
Lagrange in the right. And yeah, these two I recognize.
this guy is Euler, and who's this?
Lagrange.
Exactly. All right, now I'll give you another hint. Two of them are brothers. Actually, I'm not sure if they're brothers or they're father and son. Or maybe they're just cousins. I don't know. Up here, I'll reveal everybody. Up here, you've got two Bernoullis, Jacob and Jonathan Bernoulli. Indeed, it was Euler and Lagrange. You got Fermat, much earlier. You have Hero, or sometimes known as Heron. Sometimes Heron. And before that, you have the absolute first person who studied the minimal surface problem, Queen Dido, right? And remember, Queen Dido was given she was given a hide, the hide of a cow, and said, "You can have as much land as you like on this island that you can make on a border with this cowhide." And so she cut it into thin strips, and she just she covered the entire island. She made the perimeter out of the strip. And so she was already talking about how do you maximize area for a given circumference, or how do you minimize circumference for a given area. Hero had this idea that of figuring out that you go in straight paths. If you wanted to go back and forth across a river, you would take straight lines as if you were reflecting light. And Fermat was the one who visualized this for light with the principle of least time, which is how light moves across all media and bounces in mirrors. And then the Bernoullis, they did all this stuff on various calculus of variations problems, including the catenary and the brachistochrone, that say, what's the fastest way to fall? What's the fastest way of going from one point to another under the force of gravity? And then, of course, Euler and Lagrange, formalize the whole thing into the Euler-Lagrange equation. So these are our heroes. These are the people who, started it all. I'm sure I'm missing other people. I'm sorry if I've left out your favorite one. If I have, send me an email and tell me your favorite calculus of variation guru. Okay. So let's see if it goes forward. There we go. So I already mentioned minimal surfaces, and I don't know how much, let's just assume, what's that called? Indulge me, all right, as I tell you about them. So minimal surfaces are what happens when you have soap films. And this is what Plateau was really about. Plateau was interested in studying soap bubbles. And Plateau conjectured that in an equilibrium foam, each edge will have three faces bordering it, three faces, and they will meet at 120 degrees, and each vertex, oh, I'm sorry, my hand always does that. And each vertex, okay, so each edge does this, and each vertex will have exactly four edges coming into it, and they'll go off at 109.5 degrees, which is the tetrahedron angles. In other words, if you had a situation where you had, say, oh man, I did it again. I'm really sorry. Big hand. Okay. If you had a situation where you had an edge, like so, and you had four faces coming off of it, like so. So 1, 2, 3, 4, like so. It would actually be lower in area. It would decrease the area to take this and have it split up into two edges. Add an extra face, and then have and then instead have three faces at like this, like this. Oops, I drew that wrong. Like so. That would actually have less area. And you still have these four leaves that are coming out, these four, but they would be connected differently. In any event, Gene Taylor, it wasn't until Gene Taylor, it wasn't until Gene Taylor in 1976, look how long it took. It took more than 100 years. Gene Taylor actually proved that Plateau's rules were correct. These were true. But it was in her thesis, she proved that Plateau's rules were correct. And in the end, if you take this energy, right, you take an energy, so this energy has a surface area term with a surface tension and a pressure times volume term, that's if it's a bubble, then you can actually minimize this energy, and you discover that minimizing the energy gives you the so-called Laplace-Young rule, where there's a relationship between the pressure and the mean curvature of the surface. And so what does this tell you from the point of view of minimal surfaces? When the pressure is zero, H is zero, and it's if and only if, right? In other words, if you have a domain wall, if you have a wall, and the wall isn't being pushed in either direction, there's as much pushing on one side as there is on the other. So there's the pressure difference from one side to the other is zero, then it's flat, or at least it has zero mean curvature. So zero mean curvature surfaces come up when you're talking about a certain kind of equilibrium. And in real soap films, in real soaps, what happens is that you can have bubbles, like so, you can have two bubbles, and the pressure here, pressure 1 and pressure 2 can be different. But eventually what will happen is that air will seep from one to the other, right? So air will seep from one bubble to the other bubble. It'll get through the soapy water. And eventually the pressures will equalize. And when the pressures equalize, the interface between the two bubbles will be a zero mean curvature surface. So you can build them all the time if you want to. Okay. What I was going to show you is something that I like, is that, are they really minimal? After all, we know that when you do calculus of variations, I did it again. I'm sorry. Sorry. Are they really minimal? I know where I have to leave my hand. Minimal. Because we know in the calculus of variations, what do we know? We know that the Euler-Lagrange equations are only necessary conditions. they're not actually sufficient. And in fact, it could be that you don't have an extremal. You could have, or a minimum, I should say for a minimum, because you could have a maximum and you could have a saddle. And the thing about saddles in the space of functions is there's lots of directions in which you can be a saddle, right? You know, if you're talking about minimizing the height of a surface in 3 dimensions, well, you know, you can have a surface in 3 dimensions can have an absolute, you know, it can have a local maximum, a local minimum, or one kind of saddle. But in function space, you can have lots of saddles. So how do you know that this word minimal surface is really the right word? So Gene Taylor showed that for the soap froths based on Plateau's rules. But is there ever a case when something having zero mean curvature is the same thing as something really being minimal? And the answer is yes, sometimes. So let me just show you this nice little theorem, a nice way to prove that. So suppose M is minimal. And with minimal, in other words, H equals 0 for the surface. So it's a minimal surface, meaning H equals 0. And in some projection, its border is convex. So what am I thinking? I have some curve in space, like so. There's some surface living over it. And in the plane below, there's some plane where when I project down, I get a curve here that's convex. That's all that matters. This has to be convex. Okay? So in other words, it doesn't have to be that every projection is convex, but there has to be a convex projection. And H is 0. And one of the ways that you say H is 0 is if you look at the, excuse me, the normal to the surface, the normal, N, then you can write the divergence of N is 0. And what that would mean, let me be very explicit about that. N is a function of X and Y, right? So these are the coordinates X and Y, like so. So N only depends on X and Y. So what do I mean by this 3-dimensional divergence? Well, what I mean is that I can take N of X and Y, and I can lift it, if you like, to N tilde of X, Y, and Z, where Z is equal to H of X and Y, where H of X and Y is the graph of the curve over that convex thing. So I can always take a surface like so. It's parameterized by X and Y. And then I can always make a vector field in 3 space that's defined this way. And then I can take its divergence. I can take the divergence this way if I like to. So, but the divergence has to vanish. So suppose that this surface here, this blue surface here, M, M has divergence of N equals 0. All right, so I have a surface. It has this boundary. It has this boundary. This is dm, like so. And it's zero mean curvature. I can now show you that, in fact, this is the smallest area. So how do you do that? Well, here's how the proof goes. Look at a comparison surface. So here's a comparison surface that has the same boundary. So I look at a comparison surface, M tilde, such that dm tilde is equal to dm. So the boundaries are the same. And now if you imagine what I have is I have some kind of funky volume. I have a volume which has a red surface and a blue surface, right? So here's the red top and here's the blue bottom, like so, and it's a volume like so. And what do? That volume, inside that volume, I take this vector field n. I fill this volume with a vector field n of xy. And I can do that because everything is floating above this convex surface. So inside here, I have a vector field n of xy. And it only depends on x and y. It's constant as I go along the z direction. And I can take this and I can lift it to a set of a vector field in 3 dimensions, where n tilde is really just n of x and y. It doesn't depend on z. And by construction, the divergence of n tilde is 0. Okay. Any questions? If you're paying attention, if anybody's, it's hard to tell, you know, and I'm so far away. If there are no questions, shrug your shoulders, wave your hands, do something. If there are no questions, if there are questions, sit still. If there are no questions, wave your hands. Okay, very good. Thank you. Okay. So what do you do? How do you proceed? What you do is you say, oh, hold on. You take your surface, and in this region here, you integrate the divergence of n tilde inside this volume. And the integral of divergence of n using Gauss's law or Stokes' theorem or the fundamental theorem of calculus is the integral of n tilde on the red surface minus the integral of n tilde on the blue surface. All right, so this is dA minus dA. Well, this side's 0 because the divergence of n tilde is 0 because that's how I constructed it. So this tells me that the integral of n dot dA over the red surface and the integral of n dot dA over the blue surface are equal. But what is the integral of n dot dA? N dot dA over the blue surface. It's exactly equal to the area of the blue surface. Why is that? Because dA is equal to the vector times the unvectored area, dx, d sigma, like so. In other words, dA, the area element has some vector direction. This has some vector direction. So the area of the blue surface is equal to this integral here, which is the area of n tilde dot dA over the red surface. So the area of the blue surface is equal to the integral of n tilde dotted into n red dA. In other words, you take the n that the blue surface would have had and you dot it into the unit normal that the red surface would have had. And this number is certainly less than or equal to the area of the red surface, because this number here is always less than or equal to 1. So the area of the blue surface is always less than or equal to the area of the red surface. And that means that the area of the blue surface is actually an absolute minimum. So when you have, this is a little messy. Next time I'll have more chalk. I'll have a bigger chalkboard. Sorry, right? But the point is that you actually can, in some cases, prove that it's minimal. Literally, it's the minimal surface, but not always. Okay. Now, I've already alluded to this already. But let me just confirm that we know that there's 2 kinds of curvature that surfaces can have. Yes, of course.
Yeah. So in the last slide, where did you use the hypothesis that
ultimately you started out showing that there is some projection which goes onto a convex subset.
Oh, that is so good. Thank you for asking. So let me see if I can make more room. Let's see. Doesn't seem to let me erase anything. So let's see what I can do. Hold on. Give me a second. What's this? Okay. Okay, very good. So now I can copy what I had. I had the integral of n dot dA over the red surface is equal to the integral of n dot dA over the blue surface. And this is equal to the area of the red surface. And this is equal to the n blue dot n red dA. Did I mix these up? This is blue. This is red. Area of blue is equal to this integral over red of some number that's less than or equal to 1, dA. So this is less than or equal to the area of the red surface. Now the question, which is an excellent question, is why did I need this thing to be convex? Why did I need the projection to be convex? Well, suppose that I told you, suppose we have the following weird fact. So I'm looking down from the top. This is the top view. Suppose I told you, here's the blue surface. Now, suppose I suggested to you, which wouldn't be true, that the actual minimizing surface actually had a little appendix that was sticking out its side, right? So if I looked at it from the side, I'd have this, I'd have my blue surface, like so. And what if it had a little thing sticking out of it? Okay. Now, if it had a little thing sticking out of it, I could certainly remove that and only reduce the area. But that's only true if this is convex, right? So I could say, oh, I can remove this. I can remove this. But that's only true if the green curve is convex, because it's possible. Let me give you a different example. Suppose this is what the surface looked like. The projection looked like that. And it's always possible that there's actually a tunnel or a channel going across that surface. That might be actually lower in area. And there's no way I can argue that I could remove it. Here, right, if you try to put an appendix onto this guy, I can always say, oh, it's definitely smaller area, because by removing it smoothly, by shrinking it smoothly, I am constantly removing the area and I'm not backtracking over the surface. Does that make sense?
Am I audible? Am I
Sorry,
audible?
does that make sense?
Yes, I mean, intuitively, yes. I get your argument. One needs to do a little work.
That's correct. The little work you have to do is you take your surface, you imagine now that you enclose it inside some cylindrical region that has the same boundary. And you say, I can always, anything that sticks out of the sides, I can always remove. And it would always lower the area. Right? If I had any bit of the surface sticking out, this tube, it would always increase the area. I can always remove that. So that would be, you'd have to do a global argument first. And then from that, you would be able to say, you'd be able to do what I did. What you can't do is if you have a non-convex projection, you can't make that argument anymore because you don't know that there's a way to actually remove this smoothly. So it's not true. It's not if and only if. It's possible that there can be a surface which has a projection which is never convex, and still it's the minimum area. It's just that my proof doesn't do it. Okay, thank you. Other questions? All right, very good. Thank you. As I was saying, right, we know that there's different kinds of curvature. There's this mean curvature, which is the average of the two curvatures, and there's this Gaussian curvature. And what becomes very important in many physical systems is that you can have situations where the mean curvature is 0 and the Gaussian curvature isn't 0. You can have situations where the Gaussian curvature is 0 and the mean curvature is not 0. And you can have situations like this, but there's a sign SIGN thing. You can't have positive Gaussian curvature and H equals 0. So that tells us something. These surfaces that we're interested in, these minimal surfaces, are also surfaces where the Gaussian curvature is always less than or equal to 0. And so that comes up. That will come up as we're discussing the various physical situations. So here are some of my favorite minimal surfaces, right? And I hope they'll become some of your favorite minimal surfaces. We have here the catenoid that I described to you. This is another minimal surface which has ends. The ends of it are like a catenoid. It has catenoid ends. On the top and the bottom, but it has more stuff in the middle. And the stuff in the middle, there's a disc here. There are little handles, right? There are handles that go from the blue side to the red side, like so. See, here's an example of a minimal surface. It's minimal, H is 0, but it definitely has more area than the catenoid. It can have the same top and bottom ends as the catenoid, but still have more stuff going on. So that's the thing. The minimal surfaces don't really have to be global minima. They're local minima. And they're not even local minima in the normal sense. They're local minima only if you have a small enough patch of them. Only over a small enough patch is it a local minima. And here's another one on bottom. This also has catenoid ends. And this has four hands, four discs like this, and all sorts of handles, right? Where you go in, you come out, like so. And then here on the right is Shirk's first surface. Shirk's first surface. And this is a very cool surface, which we will come back to. This one has infinite genus. It's an infinite surface, or if you like, it's a finite surface where the space is no longer R3, but the space is the 3 torus. On the 3 torus, it's a finite thing. Okay. Now, these are interesting. They come up in soap bubbles. They come up in materials we'll be talking about. But there are also these triply periodic ones, to which I alluded. And the most famous one, in my opinion, or the most amazing one, is the gyroid. And let me tell you a story about the gyroid. Right? The Schwartz P surface, which was known forever, and the diamond surface, which was known forever, it turns out that these two surfaces have a representation. There's a complex representation where you actually have a surface in C3. And then you project from C3 to R3. Take a real projection. And it turns out that these two surfaces, the Schwartz P and the diamond surface, they're the same surface in C3. And you rotate them and you make the projection, you make the real projection, and one real projection is this, and one real oops, I did it again. I'm so sorry. I'll get it eventually. Let me rewrite that. C3 to R3. And these two surfaces are the same in C3. And they're two different real projections. And they're non-self-intersecting. And these two projections were known to each other. And in fact, if you write them in complex space, so X, Y, and Z, as complex variables, then the difference between these two surfaces is just, sorry, the difference between these two surfaces is just you take x to x e to the I theta, y e to the I theta, z e to the I theta. There's just a phase that you hit all of them with, and then you make a new real projection, you get the diamond surface. But the gyroid, it turns out, is also that surface. It's also these two surfaces. And it has a very funny phase. And you get it exactly the same way. It's just that the phase is funny. Theta is not obvious. Here it turns out theta is pi over 2. So it's just a phase rotation. But here, theta is not obvious. And this guy working for NASA, Alan Schoen, he discovered the gyroid by pure thought. And again, the cool thing about the gyroid is it doesn't intersect itself. So there's this complex surface in 3 dimensions, 3 complex dimensions, which has 3 real projections which are non-self-intersecting. And these are the 3 of them, the P, G, and D surface. And the G surface, the gyroid surface, wasn't discovered until the 1960s. So not your lifetime, but my lifetime is when Alan Schoen discovered it. And then here's another triply periodic minimal surface, which in addition to having these pieces on the these periodic cells, also has all these extra handles. Like so. If you use your imagination, in particular for the P surface, you can convince yourself that there are these units. There are these units here. Sometimes people call this the plumber's nightmare. And in fact, the plumber's nightmare is a bunch of these cells connected together into a nice cubic lattice. But if you think really hard, you'll convince yourself that there's another cell which is inside out. Instead of having yellow on the outside and blue on the inside, it has blue on the inside and yellow on the outside. There's another cell inside. It's nested in between these 8 cells, and it's exactly the same shape. The P surface divides 2 volumes of space that are actually identical to each other. It splits space into 2 pieces that are identical. So does the D, so does the G. So these surfaces are more than just triply periodic. They are bicontinuous. Well, all surfaces are bicontinuous. All surfaces divide space into 2 volumes, but it splits it into 2 equivalent volumes. So these are very special minimal surfaces, and they come up a lot in physical examples, as you'll see. Okay. And here, oops, let's see if I can show you this movie. See if the movie works. Movie working? No, oh, I see, I have to do this. Movie working. There we go. There's the P surface. And there are the cells of the P surface, and they can be rotated smoothly until they become the cells of the G surface. And the G surface cells can then be rotated to become the D surface. But do you notice that when you do this, you have to make the surface cross through itself? When you go from P to G to D, the surface is no longer embedded. So there are these 3 different embeddings. They are, to get from one to the other in real space requires the surfaces crossing, but they're just different real projections. Let's show that one again. P, G, D. Back to P. Us back to G. And I've stared at these surfaces for ages, and every time you look at them, you see something new, some new interesting symmetry, which is what Alan Schoen discovered when he found the gyroid. In any event, let me tell you what these can be used for. So minimal surfaces, what are they good for, right? So here we go. It turns out that these surfaces play an important role in understanding knitting. And I work with people. I work with a material scientist, Geneviève Dion, who has a laboratory that knits. And knitting is done by machines, for the most part, by grannies and by machines. The knitting, the movie you see on the right is showing that you actually have a structure which is bistable. You can pull it open and it stays that way. The movie repeats. And it'll just stay that way forever. But you can see on the left that you get these patterns. It's all just knitting. And sometimes you are able to create Gaussian curvature. And sometimes below it, you're capable of creating these very intricate curved surfaces. And here's what's amazing. Here's what's so surprising about this. When you do knitting, you don't have to do anything to make these patterns happen. All that you do is you choose a different kind of stitch. And there are two kinds of stitches, knit and purl. And just by choosing the pattern of knit and purl, the sweater that you make folds into whatever you like. And you might say, why do I care about this for sweaters? I don't. But these are materials. These are materials that you can design. Suppose that I had the wisdom to tell you, if you want to make something that has a particular shape, this is the pattern of stitches that you need to make. Then you can start designing things. You take these knitting machines, which spit out knit fabric, and that fabric can be yarn, it could be cotton, it could be wool, it could be carbon fiber, it could be metal wire. Whatever it is, you can now start constructing things that self-assemble themselves. It's even better, they self-process themselves, right? And so let me tell you about knit and purl. And I'll tell you about it in a way that I understand. Okay. By the way, my advisor in graduate school used to say to me, let me put this in a way that you'll understand. And so I realized that meant that I was the obstacle. So now, if it's something that I can understand, then maybe it's good. So let me show you how I understand it. Knitting, which you see here, oops, someday. Right? Knitting, which you see here, comes about by taking a piece of string, like see this piece of string, this one here, and pulling it through a loop that already exists. And you're pulling the loop from the back to the front, and you make a new loop. And then you do it again, and you do it again, and that's knitting. Purling is exactly the opposite. Instead, you have this pre-existing loop, like so, and you take a loop from the front, and you pull the loop from the front to the back, right? So knitting is pulling the loop from the back to the front. Purling is pulling the loop from the front to the back. That's why you can do it with needles. Excuse me. You can do it with needles by pulling the thing forward or backwards, whether you go clockwise or counterclockwise as you're doing the pulling. And so let me show you how it happens in real life, or how machines do it. Machines do it. So you can see all these hooks have pre-existing loops on them. And then this carriage comes across with this yarn, and the loops and the hooks pop out and pull the yarn through. See, it's pulling the yarn from the back to the front. It's pulling the loops through, and it's making more and more rows of knit. And there you go. That's how knitting works. So how does a machine do purl? How do you get purling to do it? How do you have the loop go from the back to the front? Sorry, from the front to the back. Instead, what you do for a person, that's whether you do it, whether you twist your hand one way or twist your hand the other way. A machine has an easier way of doing it, or a less elegant way of doing it. It has two beds. It has a set of hooks on the front and a set of hooks in the back. And so if you want to do knit, you use a front hook. The hook's on the bottom, pull the yarn from the back to the front, And if you want to do a purl, then you use one of the hooks on the back. So there is just called a two-bed machine, and the two beds are able to make knit and purl. And you can also have times when instead of running the carriage through, you can move the loops from the front bed to the back bed, right? The loops can the hooks can come out and grab the other loop. And by doing that, you can switch from knit to purl if you wanted to. So this is how knitting works. This is how most things that we wear, you know, most knit things that we wear are made this way. And there are rooms with these vast rooms with these machines that spit it out. Here's another movie of it if you weren't convinced, right? So this is knitting again. Or if you're looking in from the back, it's purling, like so. And here, they're very noisy. This is what the machines look like. So what I want you to appreciate when you look at that machine going is it's loud. But the other thing is that's amazing is look at the bottom. It comes out, the stuff comes out already folded. The machine isn't doing the folding. It has to do with the way that you put the knits and the purls together. So it's a weird thing. The topology of the stitches or the geometry of the stitches is controlling the final pattern on the fabric. You know, everybody's all excited about making things out of origami where you fold things and then they go out into space and they unfold and now they get much bigger in some nice way. But folding your origami, if you've ever done it yourself, is quite painstaking. And you have to do a lot of twiddling with your fingers and folding, and it has to be all neat. This just comes out folded. And so if you're looking for a material that has some three-dimensional texture, knitting's the way to go because it's very lightweight. It's a one-dimensional thing. You put in a yarn, and out comes a three-dimensional structure. And all you're doing is you're giving a set of instructions, knitting instructions. And the machines are quite sophisticated, and they go very fast. Right? And they can go faster than this. When you do laboratory knitting is done slowly because you don't want to break the needles. But factory knitting can be done much faster. And so that's fine. That's well and good for people who do knit and purl. And let me emphasize that the way that you give instructions to somebody who's knitting or to the machine is you say, oh, look at this. This is knit, different color, knit, 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 knit. And now here you say purl, 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 purl. You just give instructions, knit, knit, purl, purl, like so forth, knit, purl, whatever you like. And you're giving instructions, and the instructions are given this way. And then you come around and you give the instructions like this, and like this, and like this, and like this. So the instructions are presented to you in this linear way. However, when you're all done, you get this two-dimensional structure, which then eventually folds into 3 dimensions. And so it turns out that we were working with an artist. And this artist sent this picture to us. And he said, look at this here. He took, his name's Mike Tanis. He took metal wire, metal mesh, and he twisted them. And each of these is a helicoid. And he took a left-handed helicoid and then right-handed helicoid and a left-handed helicoid and a right-handed helicoid. And he said, look, Randy, look what I can do. I can actually put the knitting on the helicoid, on the scaffold. I can use these helicoids as a scaffold. And look how cool this is. The pink string here, the pink string and the yellow string, they're on opposite sides of the surface. So isn't that cool? The surface actually divides the knit from the two pieces of strands from each other. And why is this good? Because if you're trying to simulate or understand the structure, if you were trying to simulate, imagine you were trying to simulate individual yarns, like so. If you were trying to simulate individual yarns, you'd have to make sure that they didn't cross. No crossing. Topology is hard to implement. Right? It's difficult to implement the topology if you're doing a computation. If you're imagining modeling the yarns and the yarns can't pass through each other, you have to constantly be checking. Are they crossing through each other? And the problem with that is that that's not local. You have to check if it's crossing through any other yarn. But by dividing the yarn through these surfaces, the yarns on one side don't touch the yarns on the other side. And in these crucial places where the yarns touch, they're on opposite sides of the surface. And all the structural places, which is what makes the fabric, these crossing places, these touchings, are on opposite sides of the surface. So it suddenly makes things easier. And let me add to the story, which is it also gives me a way of understanding the picture in a way that's much more amenable to 3 dimensions, which is you look at this thing here. This is 2 strands, left-handed strands, left-handed twisting. And here you have right-handed twisting. This is right-handed. By drawing the things on helicoids, I now understand something else. I have knitting is a sequence of twisting left and twisting right, twisting left, twisting right. And purl is exactly the same, except purl just changes the parity of it. Now it's right, left, right, left. And so you see those helicoids actually give me a way to understand the structure of what's happening locally. When I look at it, I can say, oh, I know what's happening. There's a helicoid in here. There's a right-handed helicoid in here. And this right-handed helicoid is separating the strands, and the 2 strands are just wrapping around opposite sides of that helicoid. And you can say, all right, so what? Well, let me show you. So what? Helicoids are kind of cool. And this is some very old work that I did, and it's what got me excited. So, you know, I was just waiting. I was waiting for the time when this work I had done, 25 years ago would actually be useful for something. And it turned out to be useful for knitting. So here's a single helicoid. And if I want to describe the helicoid mathematically, I could say it's the level set phi equals 0 for this phi. Right? So phi equals 0 gives me a height function or a graph. Z is b on 2 pi, arctan y on x, like so. B has to do with the spacing here. So when you go around once, this surface goes up. Z goes up by b over 2 pi times 2 pi. So it goes up by b because arctangent goes by adds 2 pi. Let me erase all this. And imagine adding a second helicoid. But this helicoid, instead of being centered at x, which is here, this is x equals 0, it's centered at x equals L sub d. So it's another helicoid. It's just offset in the x direction. This is the x-axis, like so. And this is the z-axis, like so. And then I could even add a third helicoid here, right? Which is offset by 2LD. Now, if I start gluing them together, I can see that I can actually glue them together and I can get a new surface. And this surface is very neat. This surface has these lines in the front. The lines in the front are tilted at one angle, like so. That's the ones in the front. And then there are the ones in the back. And the ones in the back are tilted in the opposite direction. And so what this does is it gives me a way of interpolating between a bunch of surfaces that have one slope and a bunch of surfaces that have another slope. And in between, instead of having to just cut it in half, I actually am able to connect it, except in a few places where there's some singularities, right? There's some singularities, right? Some bad points in the middle of the surface, but they're only points. They're not whole surfaces anymore, right? And so we'd call this a parking garage, right? It's a parking garage. Right? Where you'd say, oh, right, you can park. Here's where the elevator might be. Here's where the stairs might be, and so forth. And so it turns out that helicoids can be taken and they can be put together to make new surfaces. And in fact, this very old result, so here's me doing the sum. Here is phi. I'm adding up all these different, this is a sum of arctangents. These are the helicoids. You can then rewrite this, using complex variables, if you like those. And you can then, using the product formula for sine, show that this surface can be added up, right? In fact, it can be added up into this simple surface here, like so. And setting the boundary conditions, you can actually then calculate the surface behavior. And you can look, if you like, you can look in this paper cited here. And so this makes a surface that interpolates between them. And this is, you take phi equals 0, and that gives you level sets of this surface. And in fact, it's kind of cool. This sum of arctangents, like so, actually came up in Ramanujan's notebook. In the first book. And that it adds up to this is just a result that he just states. Just, oh, that's just a fact. It turns out that, trying to see if I can see. Are you guys still there?
Yes, of course.
You guys went black. Yeah, okay. But you guys went black. The room went black.
Okay, the camera might be.
That's okay. If you're all there, it's okay. What it turns out, and we discovered this, like I said, a long time ago, is, remember I showed you Shirk's first surface? This is Shirk's first surface. And this is the sum of helicoids. And this is minimal. And this isn't minimal. However, it does have a nice feature. Since it's a sum of helicoids, it turns out the Laplacian of this function z of x, y is 0. So it's almost minimal, right? It's minimal perturbatively. Its Laplacian is 0. But here's the thing that kind of blew our minds. You can actually write the height function or the graph of Shirk's first surface this way. And you can compare it to the graph of the sum of helicoids. And you can see, believe it or not, that it's almost the same function. In fact, right? If I set b equal to 2 pi, then this goes away, and this goes away, and this goes away. And you say, look, it looks almost exactly the same. Secant alpha, arctan, y, x. And the only difference is that Shirk surface compared to the sum of helicoids has this extra factor of cosine alpha. So the only difference between Shirk surface and the sum of helicoids is a constant dilation in the y direction, which is surprising. And as far as I know, no one's ever given me a reason why it should be that simple. But there it is. Right? It comes about by actually just writing down the graphs instead of writing down some sort of implicit function, but by imagining and keeping in your head that arctangent is a multi-valued function. In any event, what's this have to do with me, or have to do with knitting? You're actually able to prove a sequence of identities, which I'm going to skip, to actually build out of this a surface that has exactly the same symmetries as the Schwartz D surface. There's no rush. There's no reason I need to rush through this. Okay. So this twist grain boundary, which is what it's called, has a certain algebraic symmetry. It's not that interesting, right? You can just see that if you make these substitutions, that the surface is invariant, right? So the surface stays the same. And if you do that, you can reinterpret this as, instead of being, let me tell you what all this unnecessary math is showing you. It's showing you, look on the left. On the left, you have a single helicoid, and I bring in more helicoids from infinity, and I build this this Shirk surface, or this surface where I've connected surfaces tilted up and to the left with surfaces tilted down and to the right, from the back to the front. So you take these helicoids, these vertical helicoids, and you bring them together. But the duality is that you can also, come on, play. Oh. The duality, sorry. Let's see if this comes. No, I'm sorry. In this method of presentation, I can't get the movies both to run. If you look at the picture on the left, the picture on the left shows you a movie. Hold on. Let me show you. I can show you by taking over. So here's the movie on the left, and you're bringing the helicoids in from the sides, and you end up with this surface. Or you can bring in helicoids from the top and the bottom and end up with the same surface. In other words, this surface here, Shirk surface, has a duality. You can either think of it as being made of helicoids stitched together vertically or helicoids stitched together horizontally. But if you're paying attention very carefully, you'll notice that this is a left-handed helicoid, and this is a right-handed helicoid. So you can either build it from left-handed helicoids coming from that are vertically oriented, or right-handed helicoids that are horizontally oriented. And you can say, so what? It means that you can actually start assembling many of these structures together. So you have a Shirk surface like so. I hope you can see my hands. If you can't, I'm gonna draw. You have one Shirk surface like so. It's this one, which connects layers like this to layers like this. And then you have a next Shirk surface, which connects layers like this to layers like this, and so on. And so you can get something that has this long 3D periodicity. And using the duality, you can actually, instead describe this as a bunch of parallel screw dislocations, or parallel helicoids, I'm sorry. Parallel helicoids, which are all either positive or negative. In other words, they're either left-handed or right-handed. And you can sum it up. And if you like doing sums and you enjoy elliptic functions, then you can actually write down a closed form expression for this surface as well. And this surface is very similar to Schur's first surface. We called it Schnurk's first surface. All right, but it's very similar. And you can say, so what? Why is this good for anything? Well, there's another way to assemble helicoids. So if I take helicoids that are all assembled in one way, all the same handedness, I get this Schurk surface. Remember, I showed you Riemann's minimal surface. All the cross sections are circles. Well, this is what it looks like. Let me show you. Let me distort it for you smoothly. If I distort it for you smoothly, so on the left bottom, I have the initial picture. And on the right bottom, I have the final picture. You can see that on the left, look at that. That's just a left-handed helicoid. And on the right, it's a right-handed helicoid. So in fact, this Riemann's minimal surface is also built out of helicoids, a left-handed one and a right-handed one. And you can say, okay, so what? Well, when I was showing you the knitting, I was showing you that with knitting is about making the scaffold with left or right-handed helicoids. And what I've just shown you is that you can put them together into different ways to make different minimal surfaces. All one-handed gives you Schur's first surface. Alternating left and right-handed gives you Riemann's minimal surface. And so these minimal surfaces, and you can write down something precise, these minimal surfaces give you a way of describing the surface between the yarns. And you can then start doing knitting on these surfaces. And what's great about that, and this is where I'm going to end today. Yeah, I'm going to end here today. What's great about that is that this surface here, this is a minimal surface. It has nice properties, the nice properties that minimal surfaces have. And also, the surface is the fabric. See, instead of thinking about the fabric in terms of these particular stitches and the particular pieces of yarn, I can think of the fabric now as the surface that separates the yarns. And so suddenly I've gone from one structure, the yarn level structure, where it's a bunch of instructions in one dimension of knit and purl, to a new kind of structure where I actually have a surface, and I can build that surface by attaching left and right-handed helicoids together. And the surface is minimal, which means that I can have explicit representations for it. And what is the consequence of that? The consequence of that, first of all, is being a minimal surface everywhere on the surface, it wants to have negative Gaussian curvature. The surfaces want to have negative Gaussian curvature. But of course, the problem is that the surface is constrained. It can't bend over on itself because it has to keep going. But on the edges, there's nothing out here. This is empty space. There's space out here too. There's space on top and space on bottom. And so what happens is when you look at a real piece of fabric that is finite and not infinite, a real piece of fabric actually gets Gaussian curvature, negative Gaussian curvature. When it's a piece of knit fabric, the top rolls up like this and the bottom rolls to the back, right? It rolls to the front. And pearl, which is the same, just look from the other side. The tops roll from front to back, and the sides roll from back to front. And you see, these are making little saddles. These are making saddles. On the inside, in the bulk, the saddles balance themselves. There's as much curvature in one direction as curvature in the other direction. There's Gaussian curvature everywhere, negative Gaussian curvature, but its orientation changes. Whether you want to bend this way, whether you want to, let me draw it like this. Let me draw it. Whether you want to have something that bends like this, or you want to have something that bends like that. You can have two different kinds, the Gaussian curvature is negative, but the orientation of the curvature tensor can be different. It can be rotated by 90 degrees. Going from knit to pearl rotates that by 90 degrees. Person I work with on this, Lauren Yu, she'd say, look, in knit, if you look on knit, most of the strands in the front are up and down. And the strands in the back, for the most part, are side to side. And she'd say, oh, that means that the blue is going one way and the yellow is going the other way, and they're pushing on each other and they're trying to make Gaussian curvature. They just can't because they're all attached to each other. And Gauss's theorem egregium says that's impossible because they can't do it without stretching, right? No stretching. I don't remember how to spell stretching. There you go. Stretching. But on the sides, there's no constraints. The constraints are released. And so look how much we've got just by thinking about minimal surfaces, right? You can say, where did we think about minimal surfaces? We realize that you can take the yarn and you can take the stitches and you can put them onto helicoids, and helicoids are minimal surfaces, and you can stitch helicoids together to get new minimal surfaces. And those new minimal surfaces all want to have zero mean curvature, and they have to have negative Gaussian curvature. And look, it manifests itself at the macroscopic scale when you knit things. I don't knit. I mean, I don't knit by hand, but I've been told that if you try to knit someone a scarf and you make it all the same knit, then the scarf rolls up funny and nobody likes it. So you always have to have knit and purl together to make sure that the scarf doesn't curl up in this funny way that happens with a patch of knit. And so where do you go from here? You say, oh, well, look at that, right? If I glue together regions of knit, and regions of purl in different patterns, lo and behold, it then folds. It self-folds into various shapes, but they're different. Let me say how weird this is. If you're a topologist, you'd say, that's nonsense, right? These knit structures that I just drew for you, right? So knitting, where you go, you pull the thing from the front to the back, from the back to the front. There are no knots here. The entire knit fabric is topologically trivial. It's the unknot. If you took the two ends and put it together, it's just the unknot. But different unknots give you different structures. And these structures are not coming about because of the knot topology of the yarn. It's coming about because you're choosing what kind of helicoid it is. Is it a left-handed helicoid or right-handed helicoid? You're putting them together in different orders. And you also get to change them top and bottom. You can go from left-handed, this is left-handed. You could switch to right-handed up here and switch this to left. You can have a transition from knit to purl vertically as well as horizontally. And so it's the topology of the handles on this minimal surface that determines the structure of the 3D folded fabric, which comes out all by itself. So now we've at least taken this problem and we've changed it from a problem in as a one-dimensional structure, how does a one-dimensional yarn fold into a three-dimensional structure, instead to how does a two-dimensional surface with a given topology of its handles, whether they're from back to front or front to back, how does that affect the structure? And let me say why this is cool for materials. So I'm showing you, you see this thing, there's a hunk of knit attached to a hunk of purl. And knit, left to its own devices, its boundaries on its vertical boundaries will roll, right? This will roll over itself like so. So it'll roll from front to back, whereas purl likes to roll from back to front. And so if you attach them together, they roll up in this neat way with each other. And look at this. Let's see if it goes. They make a spring. This spring has nothing to do with the yarn. This is made from yarn that isn't stretchy. This isn't because the yarn's elastic. This spring can be made from cotton or wool or nylon or fishing line. It doesn't matter. This spring is a spring because of how the stitches are put together, not because of the material itself. And so we get to use geometry. We have a geometric formulation now where we can talk about the structure and the behavior of this particular pattern independent of what it's made from or from what it's made. And what's great about that is that that gives you a way of understanding the structure where I don't have to know the details of the yarn. And next time, I will start showing you, I will show you how you can get these things to fold and how convincing it is that this actually predicts and describes what we see. So that's that's why you should come back next time, and I'll show you these in detail. And then we'll also switch and start talking about the gyroid phase once again. So I can't see you, but if there are any, oh, now I can see you. So you can tell me if there are any questions for today. And like I said, feel free to email me tonight if you have any questions that come up.
Okay, so
Thank you so much for the fascinating talk. Yeah, if there are any questions, please ask right now or later.
okay, there are some few questions.
Hello, sir. Am I
Yes.
audible?
Yeah, I can hear you.
You have said in a some way, summation of helicoid we reach to the first surface.
Yes.
So the question is first surface is conjugate to fifth surface, that is a tower, and helicoid is conjugate to catenoid. And like intuitively they look if we add catenoid we can get to the first surface. So is there a way or it's just an intuition?
This is a question that I actually thought about very hard with Dr. Day a long time ago. The thing I'm doing, well, let's see if I can figure out how this works. I think I can do this. Let's see. Yes, yes. Okay. So this trick of adding together helicoids, I'm adding them together in a totally different way. I'm not treating them as, so what you were asking me was if I could talk about the Weierstrass-Enneper representation of a helicoid. Oh man, I did it again. Hold on. I could talk about one representation of a helicoid where I have X of some complex variable squiggle and Y of squiggle and Z squiggle. and squiggle are some sort of coordinates, two-dimensional complex coordinates. Right? Complex coordinate. On the surface. And when you talk about conjugation, and when I mentioned it about the P surface and the D surface in the gyroid, that is using this representation, the Weierstrass-Enneper representation. And it's very elegant, but you know, being a simplistic physicist, I wanted addition to really be addition. And so you see, all we did here is we said, well, this thing here, this thing, if I look at level sets of phi equals 0, if I look at a level set of phi, this gives me one helicoid, and this gives me a different helicoid. And all I did is I took these guys here, and I added them up. I added them like so. So here's the sum, and here's Z. And then I'm looking for a different way of representing my surface. I'm representing the surface by the level set phi equals 0. It's a totally different way of doing it. And to do it, right, on the one hand, when you do Weierstrass-Enneper, when you have Weierstrass-Enneper, the way that you get periods, right, you had X of squiggle and Y of squiggle and Z of squiggle. These periods come from doing elliptic integrals. Right? How do you get something that's periodic? It comes about, you do the integral on the complex variable squiggle, and you go around a cycle where there's a branch cut, and it gives you X gets shifted by something, the same way that you get that for elliptic functions and so forth. Here, I'm using a completely different representation. I'm using the fact that arctangent is multi-valued. So I give up this nice complex representation, where these variables squiggle. It's very hard to draw what the variables are. It's very hard to look at the surface and say, these are lines of constant, you know, real squiggle and imaginary squiggle. Here, I switch it. So now I know what the coordinates are. I know what all X, Y, and Z mean. But I have to be really careful that I have all the branches of arctangent. So if you like, this is a local description, local plus global sewing, which is how we make all the pictures, right? So we get Mathematica to draw one blob, and then we just copy it, right? So yes, it's a totally different way of doing things, which is useful for us. And like I said, Dr. Day and I thought about this for quite some time. Right. The question is how to make the connection between this kind of representation and the Weierstrass-Enneper representation. So it's a different kind of way of adding things together.
Okay, thank you, sir.
Sure.
Are there further questions?
I have a question. Like many years ago when we met, you had also mentioned that these gyroid-like or Schwarz-P-like surfaces are actually equipotential surfaces inside crystals. Is that, if I remember correctly?
That's correct. Yeah.
So they appear as...
Yeah, next time I will give you a general argument for why you expect triply periodic minimal surfaces in materials. It's a very elegant argument due to Robert Hollisch and coworkers. And then I will start showing you materials that have triply periodic minimal surfaces as their dividing surfaces.
I see. So if there are no other questions, let's thank Professor Kamien for this fantastic talk. And yeah, so
Thank you. And I'll see you tomorrow